Because first of all, you need to understand the mathematics. You need to understand the fundamentals. And what I always say in my class is that you should not use a complicated model for the problem that you want to solve. You should first understand the simplest possible model that you can use, see where it comes from, see how far it can reach you, because most of the times it's going to be enough. You don't need to go for the largest deep learning model or the most complicated approach. That's going to be more expensive, harder to train, and you will not learn anything in the process. You will learn when you're trying to implement something from the basics and you understand the mathematics.
Welcome to a new episode of the Engineered Mind podcast. I'm your host Yusuf, and on this podcast I am talking to researchers, scientists and engineers and how their work is shaping the world around us. For this episode, I am very excited to talk to Dr. Ricardo Vinuesa. Ricardo is an associate professor at the Department of Engineering Mechanics at KTH Royal Institute of Technology in Stockholm. He is also a researcher at the AI Sustainability Center in Stockholm and vice director of the KTH Digitalization platform. He received his Ph.D. in Mechanical and Aerospace Engineering from the Illinois Institute of Technology in Chicago. His research combines numerical simulations and data-driven methods to understand and model complex wall-bounded turbulent flows, such as the boundary layers developing around wings, obstacles, or the flow through ducted geometries. He has led several international initiatives within sustainable and interpretable AI, which have led to highly influential articles in literature. In this podcast, Ricardo and I talk about the fundamentals of turbulence, AI for fluid mechanics, the status quo, and what it promises to solve in terms of simulations. We talk about data and where to get data from for these type of simulations. We talk about simulation in general versus experimental testing, the pros and cons of it. We also talk about verification and validation in computational fluid dynamics, but also why black box models need to be understood. So we cover explainability and interpretability, what the difference between those two approaches are and why they are important. Last but certainly not least, we will also cover sustainable AI and so much more. If you would like to support this episode, make sure you give this episode a like and leave a comment down below to make sure the ominous algorithm is suggesting the video to more people. Subscribe if you haven't already. And now, ladies and gentlemen, here is my podcast with Ricardo Vinuesa. Ricardo, welcome to my show.
Thank you very much. It's a real pleasure to be here, and thank you for the invitation.
Yeah, sure, no problem. It was really a pain to actually schedule this meeting because you're busy, I'm busy, so finally we made it. Today we'll talk about a very exciting topic, which is machine learning for fluid mechanics. But before we jump into that, and we have to cover a lot of questions in 1 hour, can you give the audience maybe a 1 or 2 minute bio? Who is Ricardo and what do you actually work on?
Yes, so my name is Ricardo Vinuesa. I'm an associate professor at KTH in Stockholm, Royal Institute of Technology. I work with mostly with high-performance computing, so large-scale simulations of turbulent flows in complex geometries. And I also work with machine learning, with data-driven methods that can be used for modeling, for predicting, for controlling, and trying to understand a bit more of these complicated flow configurations. I'm also very interested in aspects of sustainability and how these new technologies, simulation, data-driven, artificial intelligence, can really help us to achieve some of the sustainability goals of the United Nations, which is a quite important and urgent context that we have as well. And I'm generally quite interested in complex engineering problems that require mathematics, computers, some interesting physics going on. So I really like this sort of multidisciplinary research.
Really cool. Yeah, we're getting a lot of questions on AI for fluid mechanics, which starts from the very beginner level. So people just getting started maybe in their bachelor's, but love fluid mechanics and would love to know where machine learning is bringing them, if it's enhancing CFD, if it's substituting CFD. And obviously we also have the professional side of things, like talking about all these networks, what kind of networks can be used. But yeah, let's start maybe from the beginning, Ricardo. Mm-hmm. Let's define turbulence. What is turbulence and what is so tricky about it?
Yeah, turbulence is a state of a flow, of a fluid flow, in which the motion of the flow is chaotic. It's chaotic, and therefore, what is interesting is that there is a certain structure underneath the chaotic motions, and we are now with supercomputers and since the 70s, 80s, starting with visualizations, but now even more with the capabilities of analyzing large databases, trying to learn more about that structure underlying the chaotic behavior. But it is very relevant in many applications. not only because of the complexity of this problem. I mean, let's remember that is the unsolved problem of classical physics, classical mechanics. So it's really, and of course, Richard Feynman had very nice quotes, also about turbulence and the complexity of turbulence. So it is a very interesting problem from the scientific point of view, but also when it comes to the drag that is present in many the surfaces of many vehicles when we are trying to transport oil, which is nowadays quite a trendy topic, an important topic, unfortunately, due to the current political circumstances. But also if we want to understand atmospheric boundary layers, the nature around us, the atmosphere and the oceans, all these phenomena are really very tightly connected to turbulence. So being able to understand this flow and being able to, why not to control it and to manage the behavior of this flow is actually very important, with the possibility of hopefully trying to design better engineering solutions, but also understand a little bit more about our planet and the current climate emergency that we are suffering.
Very interesting. So we have been solving these nonlinear partial differential equations, namely the Navier-Stokes equation, for many years now, and scientists have spent a ton of time on that, thousands of PhD theses and whatnot. So the question might arise, why would we even bother using artificial intelligence solving fluid flow simulations? Why try in the first place?
Yeah, that's a good question. And coming back to what you mentioned and many of the questions that were sent, of whether artificial intelligence can replace CFD, I mean, I really think that we are not going in that direction. I mean, artificial intelligence will not replace CFD. Let's try to understand a bit what we are doing. When you're solving the Navier-Stokes equations, you have a set of partial differential equations that you can discretize and solve numerically, integrate in time numerically. And there are, of course, very well-established methods to do that. So we are not trying to replace those methods, because you're not going to find a more efficient way of solving those equations numerically than with the well-established methods that already exist. So it's not about replacing CFD. What we are trying to do, and that's what we also highlight in the recent perspective paper together with Steve Branton that we just published in Nature Computational Science, is that there are several niche applications where machine learning can help. So it's not really about replacing CFD. It's more about being able to find those applications where we can use this technology to get better or more efficient results. And we find three different areas. We talk about accelerating simulations. We talk about improved modeling, both of RANs and LES, and also more robust and better reduced order models. So in these three dimensions, we really see that there is a possibility to improve and to have benefits from the artificial intelligence technology. One example, why we are not replacing CFD. What we see, of course, there are many pressure correction methods to solve the Navier-Stokes equations, in which you need to solve a Poisson problem that might be very computationally expensive. And then maybe what we have also seen in some of the literature and some of our work is that you can use machine learning algorithms to make that part of the solution, the Poisson solve, more efficient. So perhaps within the whole algorithm that you're using to solve the Navier-Stokes equations, the Poisson solve can be done via machine learning, or maybe you can even use traditional methods to solve the Poisson problem, but the initial condition or the initial estimations for that solution can come from machine learning. So that's one example of how you can actually use established methods, which you are not going to beat, you're not going to be more efficient than those, but using machine learning, you can get more efficient overall solution times. Perhaps another example of how one can use machine learning to solve these equations or to have to solve those equations is a recent article that we have today with Javier Saibasi, we just published it in Physics of Fluids, to use physics-informed neural networks, SPINs, to solve the RANS equations, the steady RANS equations. What is the advantage of that? Well, first of all, we formulate the 2D steady RANs. So we have a certain generality of the problems that we can actually solve. And we use spins to solve all the terms in the equations, given appropriate boundary conditions, without having to come up with a model for the Reynolds stresses. So we don't need to rely on any viscosity assumptions or any other model that you want to generate for the Reynolds stresses. You just solve everything through pins. And in some cases, like in this one, you can have a more efficient solution than with a traditional method. Why is that? First of all, we don't need measure solutions as fine as those that you would need with a traditional solver for runs, because pins rely on automatic differentiation, and therefore you have the gradients exactly resolved. So you don't need to resolve all the gradients with a measure solution. You can get away with a coarser mesh, which gives you an advantage over the finer mesh that you would need in a commercial code. The disadvantage of pins, you still need training. You still need to match the boundary conditions. You still need to minimize the residual of the Navier-Stokes equations, which is done in a way that is less efficient than with a traditional CFD solver. So if you compare the traditional approach and the pins, the computational cost is very similar because we have a coarser mesh, but a more expensive method. And we have one benefit, and it's that we did not have to rely on a negative viscosity model for the Reynolds stresses. We just solved the Reynolds stresses as part of our equations. So we have actually obtained very, very good results using pins, errors of less than 1% in the Reynolds stresses in cases with pressure gradients, with curvature, even with separation. So we have actually obtained very promising results. It's an interesting direction. And as you can see, we are not replacing traditional runs. We're just finding certain niche applications where pins, in this case, or other machine learning methods, could actually help and complement the traditional approaches.
Mm-hmm. Very, very interesting. And we'll talk about pins and all the branches that you've mentioned at a later point in time. So I think also one of the papers, which is, by the way, has a beautiful title, which talks about enhancing CFD with machine learning, not actually substituting CFD with machine learning. You talk about this kind of hierarchical structure. So deep learning has the ability to learn basically at the initial layers will learn the simple relationships, and then the deeper layers will basically learn the extract more information or more abstract information from those relationships. And then the physical problems that you talked about have exactly that kind of hierarchical structure that you talked about. So it's actually a perfect fit for what you've just mentioned. Maybe you can talk a little bit more about, when we think about machine learning, obviously we need data. And what I would like to do with you, Ricardo, during this podcast is we start with data, talk about models, and then also about post-processing interpretability and explainability of those models. So let's start with data. People, 100%, I know for sure the question will come, where do I get my data from? Do I use CFD data that I've generated myself in the simulation? Where do I get data from?
Yeah, I mean, depends a lot on the problem that you're trying to solve. And you don't always need massive amounts of data. If you have a certain problem where you're trying to optimize and you're using reinforcement learning or some gradient-based approach, then you just need enough data during your simulation to be able to optimize, to make the optimization that you're trying to do. If you're having so that would be a reinforcement learning sort of approach, or in an unsupervised approach, you don't probably need so much data. If you have a supervised approach where you really need to make some mapping, then you're going to have more strict requirements when it comes to the amount of data. And it strongly depends on what you want to solve and the type of problem that you want to do. Some of the problems that I have been working on have to do with non-intrusive sensing. So in that sense, you want to, let's imagine that you have a wall, no? You have the turbulent flow above the wall, and you want to see what happens above the wall based on measurements at the wall. That's why it's non-intrusive. You don't put the sensor on the flow, you put the sensors at the wall. And then we have been able to develop very good, actually, and very accurate models to correlate what happens at the wall with what's happening at different distances above the wall, either in the near wall region, in the outer region, farther into the wake. And that's interesting because if you want to do opposition control or closed loop control, you want to know what is happening to the flow at each instant so that you can define a control that better opposes it. And to do that, if you can measure at the wall, if you can sense the flow at the wall and then connect with what's happening above, then you are actually able to have a pretty good model, no? A pretty good mapping of the status of the flow to be able to control it. For this type of application, we have been using DNS data, which is, of course, expensive, computationally expensive. But then you have a model that is already trained and very quick to evaluate that correlates those local measurements at the wall with what's happening in the bulk of the flow, basically. Of course, if you deploy that in an experiment, and that's something that we are currently doing, the DNS data is going to be not so representative of the actual situation in the wind tunnel, because in the wind tunnel you're going to have less resolution, you're going to have certain measurement errors, and that's something that we are also working on incorporating. So when you have your model that is trained on DNS data, you can try to include some of the limitations of the experiment so that we are actually having a tool that can be helpful, matching the characteristics of the experimental data, and that it can be evaluated also in real time. Another thing that we should keep in mind when it comes to the amount of data that you're using is the concept of transfer learning, which is not so widely used yet in the fluid mechanics community, but we should certainly keep it in mind. And it's the fact that sometimes you train a model for a particular problem, for a particular application, and you can actually use most of what has been learned in that problem for a different one. So you don't need to start your training from scratch, but you can actually reuse most of the stuff that has been learned for a new configuration. And this has to do with what you mentioned before about the hierarchical learning. No, I mean, the first layers are able to respond and to detect features that are more abstract in the data. And we are lucky in the sense that in Turbulence, we have very pronounced extractors that we can, they're associated with spatial correlations that we can exploit with our deep learning models. And these simpler extractors or simpler features are hierarchically building more complex elements in the flow. And that's how the network is learning. The network, as you go deeper into the network, is learning more and more complex relations between those more abstract elements due to the concatenated application of all the convolutions, if you have a convolution neural network. So that's why transfer learning is actually helpful, because you can freeze certain layers because perhaps some of these more abstract features are very similar in different flow cases, and retrain only the last layers that are able to capture the details of the extractors that may change from one case to the other one. Just to give you an example, we have been using a network for non-intrusive sensing at Aritau 180, Reynolds tau 180, so a quite low Reynolds number. And through transfer learning to a higher Reynolds number, a Reynolds tau of 550, which computationally is much more demanding, we could reduce the amount of training data that we needed by a factor of 4, so only 25% of the original data. So, of course, if you think of the data generation required for that new case, well, we have really saved significantly in terms of computer time, and we're actually able to minimize the amount of required data. So this is just one example, but just to give you perspective on how we should actually be aware of the need of data, but also on of the tools that we have to reduce as much as possible the data that is being used for our applications.
Interesting. You have been a former experimentalist, if I'm not completely mistaken. So you basically switched during your studies or during your master's to simulation. My question would now be, when we talk about the wind tunnel, which is, by the way, a beautiful example, you have this kind of intractable physics, and you have the car in the wind tunnel, and you try to maybe use machine learning, whether that's on a CFD simulation or maybe in the real world from test data or sensor data. Where do you see the differences using machine learning for CFD simulations on one side, and then using it for experimental setups?
Yes. I mean, it was, as you mentioned, I started, actually during my master's, I did mostly simulations. Mm-hmm. Then at the beginning of my PhD in Chicago, I was starting to do experiments, and then I went back to simulations. So I went a bit back and forth, but I enjoy both types of work, and it's actually very, very fun. No? Everything that has to do with turbulence and fluid mechanics is always very exciting. I would not differentiate necessarily applications of machine learning to experiments or to CFD. Mm-hmm. It's more about the type of data that you have and the type of problem that you are trying to target. If it's a problem that has to do with optimization, with prediction, then you will have both experimental or numerical data that you can try to use for the application that you want to have. Of course, in the simulation, the data is going to be of higher resolution, typically, and of higher accuracy. And in the experiment, you you may have experimental limitations in terms of resolution, in terms of noise, in terms of deflections of the probe, correction of the probe position. There are many things that one needs to be aware of, but perhaps you can have much longer time series, no? Because you can acquire more and more data. So in a way, it's important to be aware of the limitations that you have with the data set that you're having, and not worry too much about the type of data if it comes from an experiment or from a simulation, but more on the application that you want to have. And one approach that is actually quite promising is that of multi-fidelity. You know, you can actually focus on applications where you have data of different levels of fidelity. Perhaps the DNS has the highest fidelity, then you may have different types of simulation of less fidelity. Perhaps experimental data has less resolution, so it could be considered to have less fidelity, but you can explore more cases. No? If you want to, let's imagine that you want to characterize a certain airfoil, no? And you want to look at the different angles of attack, and you want to look at different Reynolds numbers, and then you can do many experiments in many of these configurations, but you don't get so much data in each of those cases. And then you can do few DNSs, and you can do some LESs. And at the end, what you want to do is build a model that takes into account all the information, perhaps giving more weight to the data of more fidelity, but also exploiting the breadth of data that you can get from the other approaches of less fidelity. So I think that's also a quite promising approach. It's a bit of a more statistically oriented approach, but that can be combined with modern deep learning approaches or other data-driven methods that one can consider nowadays.
Mm-hmm. As an experimentalist, would you say that assuming that you would perform the test in the right way, and maybe you would do a CFD simulation, have like both engineers are perfect in what they do you think one complements the other? Because you could say, well, CFD is error prone because we build a model of a model, we have the numerics integrated into them, we could make a mistake in terms of modeling, what kind of numerical schemes we use. But then we have the experimentalist where maybe there's kind of a bit of noise in the time series data. How would you differentiate those two? And maybe you have your own thoughts to that as well.
Yeah, I mean, they certainly complement each other. And one can, if we think of a simulation of the highest fidelity, so we don't have so many modeling errors, no? Because in the end you do a DNS and it's very well resolved, and an experiment of the highest fidelity. So still you will have some limitations, but probably you will be able to conduct the experiment with a time horizon that is much more manageable. Then one way to combine both approaches is to use the experiment to maybe explore a wider range of configurations, more Reynolds numbers, more geometries, even that you can change the model and try another geometry, whereas maybe the DNS takes months to complete. No? So perhaps you can combine both. You can see for one or two particular configurations with the DNS, you can try to understand all the details of the last vortex of the flow and track the vortices and make a very good model of the coherent structures and really see all the effects that are present in the flow. And then if you want to generalize those conclusions a bit with experiment, where maybe you cannot solve all the vortices, but you can see the overall features of the larger scales, you can try to take those conclusions and those models that you got from the DNS and extend them to cases where other factors come in, you have more complexity, and you have a much wider range of conditions. So I would say that, of course, you can use them synergistically, so you can actually combine the advantages of both simulations and experiments, and very importantly, being aware of the limitations of each of them. Yeah. So if you're doing experiments and you're comparing with experiments, you should go back to the articles to see exactly how the measurements were taken, what are the limitations of those measurement techniques, and if you're doing a DNS or if you're doing some model simulation, that you're aware of the modeling assumptions and what are the potential problems and attenuations, for example, that you can have in those simulations.
Yeah, very interesting, Ricardo. And one thing you talked about earlier on was like the 3D wall-bounded turbulent flows, where like the production of the TKE is basically close to the wall. But then maybe there's some kind of idea that maybe in the future CFD engineers will kind of have a help or recommendation tool in their CFD tool, whatever they use, which tells them how to maybe what type of mesh they should use, or maybe the machine learning model maps from the wall to maybe to the far region of the wall. Some kind of application like this. I'm not sure. Maybe you know more about that. What's currently being researched on in terms of like TKE and whatnot, and how it can help CFD engineers in their industrial work rather than working on Poisson equations and things like that. Yeah.
So of course the problem of wall-bounded turbulence simulations, as we increase the Reynolds number, is that the separation of scales increases significantly, and therefore the region close to the wall becomes very, very small. No? So you need very high computational resources, very fine meshes to be able to resolve that region close to the wall. And that's where, I mean, at moderate or moderately high Reynolds numbers, most of the production takes place. At high Reynolds numbers, then you also have production in the outer region, but at moderately high Reynolds numbers, most of the production is actually close to the wall. And that's what makes the simulations extremely expensive as we increase the Reynolds number, and what makes them unfeasible if you want to do a DNS of a real application. And then, of course, we enter in the topic of wall models. I mean, there are possibilities to replace that region close to the wall with a certain model. You can assume what is happening there, or you can have an off-wall boundary condition or some sort of assumption just to try to not resolve in such high detail on that region. That's done very often in atmospheric boundary layer simulations, because, of course, the Reynolds number are huge. And there are some limitations of these models, but also some merits that one can actually cite. And these methods are used for these very large Reynolds number simulations, and they have some degree of success. Perhaps an area where I think that machine learning can help is in improving the definition of those off-wall boundary conditions. So this is my wall, right? And then you have the near wall region where you have the near wall cycle or most of the production, and that's the very computationally expensive region. And you want to set a boundary condition above that, so maybe at the beginning of the overlap region. So you want to really save all of this, which is going to be most of the computational cost anyway. Then maybe you can develop techniques to devise a better method to create this boundary condition that is set at the beginning of the overlap region. And maybe, there is some work now. Petros Koumoutsakos, for example, he has been working on reinforcement learning to be able to set this boundary condition. We have some work also using CNNs and GANs to be able to predict what to put here based on what happens above. So correlating the flow kind of like deep into the overlap layer with what you would need to have at the beginning of the overlap layer to have a proper boundary condition there. And there is some progress, and there is some interesting directions that we are experiencing. But I still think that there is some work to be done, because the thing is that we still don't know exactly what that boundary condition would look like. It's not really what you will have on that plane in a DNS, because of course your simulation is coarser than a DNS, so now you don't have exactly what you would get in the DNS. And filtering the DNS is not enough, because when you start to filter, it's not the same as a coarse simulation with that is missing the physics that you are not having in the simulation. So nobody really knows exactly what you need to put in that boundary condition, but that's where machine learning is starting to help us. And the supervised approach has some promise, but at some point you don't know exactly what you should be putting anyway in the first place. And the unsupervised approach might actually give us some insights into what should be the condition to put there. So I think there is quite some promise, and we have some ideas on what to do. It's one of the areas where we are actually working as well on trying to develop better world models. And certainly, if such an approach is established and it's robust enough, that can be of very much help to industrial applications, of course.
Very interesting. Thanks for the insight, Ricardo. Now, one of the questions would be, a lot of people take, for example, Coursera courses in machine learning and AI, like the classical courses that we all know about. Now, then they might ask, okay, how is a network that I'm building for my fluid flow simulation and extracting fluid flow features, how is that different from the network I'm learning from a Coursera course, for example? Maybe you can talk about a few different models that engineers can use to actually use AI for CFD.
Yeah, I mean, I think the Coursera courses in general, they're very helpful, and they are very good in giving you the fundamentals and some of the... So on the one hand, the fundamentals from a mathematical point of view, because you need to know mathematically what is going on, and also to give some hands-on experience on simple architectures that you can really see what a neural network is doing, what it is, what is not. And there is a lot of debate nowadays, if you look at the media, all the hype that is happening around deep learning and machine learning, that's not productive at all for research and for development. But certainly that you can learn some of the basics from the fundamental point of view and from the perspective of what it is really to program a neural network or to implement a neural network. And then from there, you can actually start to build up. And luckily nowadays, there is extensive material in GitHub repositories. There's every day hundreds of papers being published on different architectures and different strategies. So we are lucky to live in a time where we have the availability of resources where almost by yourself, you can really learn a lot. Of course, the community is very helpful, because then you can really get guidance on which directions are more promising, which ones are less promising. But I think that starting with a Coursera course to give you some background or some basic course that you can have in any resource online can be a good starting point. I have at KTH, we started last year a course on machine learning applied to engineering mechanics. We are in the Department of Engineering Mechanics. So we started that course last year. It was quite successful. Now this year we are having a bigger edition. And we start with quite classic data-driven methods first. So we start with Ph.D, with PCA, with DMD, with methods based on algebra. Because first of all, you need to understand the mathematics. You need to understand the fundamentals. And what I always say in my class is that you should not use a complicated model for the problem that you want to solve. You should first understand the simplest possible model that you can use, see where it comes from, see how far it can reach you, because most of the times it's going to be enough. You don't need to go for the largest deep learning model or the most complicated approach. That's going to be more expensive, harder to train, and you will not learn anything in the process. You will learn when you're trying to implement something from the basics and you understand the mathematics. So, and that's what we try to do also in the research. We start with simple models first, and then we try to increase the complexity as we need it. How do they look compared with the networks that you would have in Coursera? I mean, at the end, I think that the biggest advantage of fluid mechanics is that it's an environment that is very data rich. So we certainly have, either if we do simulations or experiments in both areas, we have a lot of data, and the flow is rich enough in terms of temporal and spatial complexity, such that we can exploit the correlations that we have in the data. So even a very simple recurrent neural network that can help you to exploit the temporal dependencies is going to be very, very good or very promising for many applications in Turbulence. Now we are having much more complex architectures, and the same with the spatial information, with the coherent structures that I was mentioning before. You can go to a very simple CNN, a convolutional neural network, where you can actually try to learn from the spatial distributions of these structures and make meaningful predictions of the flow. So I think that starting from very basic models and little by little building towards more complex and more modern approaches is usually a good idea.
Very cool. Yeah, I will put a link to some papers and also GitHub repositories in the comments down below. And if people have any questions, feel free to reach out to Ricardo via Twitter. Cool. When we talk about the interpretability of models, and I want to put it into split it into two segments. On the one side, we have the verification and validation of the solutions that you get out. And on the other side, we have like the explainability/interpretability, and what the difference between those two terms is. Maybe let's start with the verification and validation, Ricardo. How do you usually do that?
Yeah. So, I mean, if we think of CFD first, I mean, of course, there is the whole area of uncertainty quantification where you can try to have robust models to really assess the different sources of error of your simulations, And you can have statistical errors, you can have modeling errors, and then one can actually look at sensitivities of the results to many of the parameters that you have, including the resolution, the filtering parameters, and this is all very well established areas, which experimentally, it's interesting because in the experiments we have been using all these UQ techniques for quite some time in a quite robust manner, and only more recently we are actually starting to apply them more to simulations. I believe it's essential. You cannot report a result, a profile in a paper without an error bar or without a proper assessment of the uncertainty. If we look at neural networks, there is also quite an interesting area, and there is, of course, the framework of probabilistic neural networks. We have some work also where we have been looking at stochastic weight averaging of the parameters of the networks. So one needs to be able to train different networks, starting from different initial conditions or initial values, and be able to, in a way, compile the information of the parameters from the various networks to get an uncertainty curve on all the predictions that are obtained from the network. The point is that at the end, we have our weights of the network. We have a distribution of those weights based on the various networks that we have trained, and that when we make a certain prediction, we also end up with a result, but also an error bar associated with that result. And there's, from a statistical point of view, there is a good formal framework to do it. And of course, in the context of training of machine learning models and deep learning, it's being now adopted and implemented. And in applications where you're having quite sensitive behavior and quite some dependencies on initial conditions, on perturbations, on fluctuations, it's very important to be able to assess this level of uncertainty.
Interesting. When we now talk about the differentiation between explainability and interpretability, could you maybe first explain why are they so important? Obviously, when we talk about medical applications, nobody would use a model that's not explainable or interpretable. Why would we even care as engineers then for AI for fluid mechanics?
Yeah, so I mean, we can talk about the difference between explainability and interpretability maybe later. It's a subtle difference, but it's very important. So I think it's good to discuss it. But in general, why should a model not be a black box? No, I mean, it's in general, of course, for medical applications, it's obvious. Even for other applications that have social implications, like if we are thinking of whether a loan is going to be given to a client of the bank or not. Or if we think of data-driven methods associated with digital contact tracing, for the COVID-19 pandemic, whatever decision is being made by an algorithm, you need to, first of all, have the right to contest, that you can discuss with a human that is really behind taking responsibility of that decision, and second, to be able to investigate what's happening with that model and why a certain decision has been made. This is essential if we are deploying data-driven methods that have implications in our lives. If we think of fluid mechanics, we can certainly get, again, in tremendous insight into the physics and into the processes that are happening. So if we are talking about non-intrusive sensing, and we are able to connect what happens at the wall with what happens above the wall, well, we can have a neural network that is trained to do that, and we can actually get very good results. But then if we can come up with an expression that is giving you, it's reproducing the results of that deep learning model, we can actually maybe learn a lot about the physics. We can see, okay, but to make this prediction, the sort of structures that are more important are the ones that are attached to the wall, because those ones have reproduce the linear behavior of turbulence, which has to do with superposition. But then in addition to it, we have other nonlinear mechanisms that are also part of my model. And when the model is interpretable, I can see it. And those nonlinear interactions are associated with the modulation. And the modulation is a multi-scale phenomenon, and we can actually see what are the different frequencies that are involved in this modulation. And through this process, we can actually try to learn a lot about the physics and a lot about the predictions that we're actually making. So I would say that the first reason is to learn about the physics, and the second one is for robustness and reliability. I mean, if you're putting this algorithm in an airplane, and we want to have flow control on the fly in the airplane, would you trust more this black box application that you don't know what's going on, or an equation? Well, probably having the equation and investigating what the equation does in extreme conditions, because of course, in the deep learning model, you cannot test all the range of conditions, or maybe you can test it, but it's much more cumbersome. No?
Yeah.
If you have the equation, you can see how the model will react in extreme conditions and maybe design for safety and robustness in a more meaningful way. So for sure, even in fluid mechanics applications, the models need to be interpretable and or explainable.
Yeah, that makes a lot of sense. When we talk about also like predictions in general, or like data storage, when we talk about these machine learning applications, where do you see the biggest bottlenecks at the moment in terms of computational speed and also data storage in general?
Yeah, that's a problem, everywhere in terms of storage. And I think that we have been experiencing that problem. Every supercomputing center that you talk to, they're having the same issues, no? We are really increasing the speed of the HPC centers, no? So we have much larger machines, much more computation power, much more capabilities. But of course, the data generation increases the same proportionally to the amount of computer power that you have, right? So if you increase the computer power by a factor of 10, but the storage by a factor of 2, then you're going to be in trouble, right? So perhaps we should also raise awareness about the need of having adequate storage policies. That's one part of the problem. We should have adequate storage policies. However, we should also be aware of the fact that if you increase the storage, you're going to feel it again, right? Because this is like when you buy a bigger apartment, no? Because if you buy a bigger apartment, you're going to fill it with things anyway.
Yeah.
So you should also change a little bit the mentality that you have when you are performing simulations and look at what data is actually necessary to be stored in the short term, in the long term, how you can design your algorithms in a better way to have a much more efficient storage. For example, when you conduct a turbulence simulation and if you want to focus on reporting turbulence statistics, then maybe you need to store thousands of 3D fields and then based on those fields, calculate the statistics. You can calculate those statistics on the fly. And then at the end, you will get much smaller files that are exactly what you're looking for. You don't need to really store all this information. Or maybe you can have some instantaneous fields, you can have some time series that can help you to calculate certain quantities, but you don't need to have all the data in 3D in every single instant of the simulation, because that's what really takes a lot of data. And then there is, of course, the possibility of compressing data, which is another area which is important in computer science. Also, in the context of machine learning, there is quite some potential. And if we think of autoencoders, for example, that have been very successful in compressing data very efficiently and very large databases, that's another promising approach. So perhaps the storage is not only about the amount of storage, but also about the mentality that we have when doing simulations, that we should really be aware of what really needs to be stored in order to optimize our requirements.
Mm-hmm. Interesting. Talking about mentality and also about computational speed and saving all this big amounts of data, we also have to mention sustainability. And that's one of the topics that you mentioned earlier on. As obviously some of the companies we see out there, like with big news coming out, you have billions of parameters in your neural network. Sometimes people use this kind of power because they have the power at their fingertips, but sometimes we don't actually need to do that. So what kind of promises do you have, or kind of visions do you have for the future? How AI or like computational power can be used more efficiently to empower a sustainable future?
Yes, that's a very good question. So this is the usual question about AI for sustainability. And of course, there is quite some work on it. We have a review paper that we published a couple of years ago in Nature Communications, where we reported that AI can really help achieve most of the sustainable development goals and the targets of the SDGs. There are also some negative effects that one needs to be aware of. And we should not forget that the electricity consumption of ICTs, so information and communication technologies, is currently around 2% of the total electricity, but in 10 years, it's expected to reach 20 or 30% of the total. So if we think of the magnitude of the change in only 10 years, it's actually mind-blowing. No? And there is a problem when we are not thinking of the sustainability of AI. So one thing is AI for sustainability, but a very different and important one is the sustainability itself of the technology. No? And I think in that sense, the HPC community, the high-performance computing community, I think that it has been more aware of the cost of the simulations. I mean, when you use 50,000, 100,000 cores for several months, clearly you're using massive amounts of data and computations. And when you get a computational project in a large supercomputing center, you get the equivalent in money of that simulation and the equivalent in CO2 emissions. So how much impact you're having in the environment by doing that simulation. Because of course it's very easy to be with your laptop and press the button and submit as batch, and then you don't think of the thousands of processors that are working and the amount of electrical power that is being consumed to run that simulation. when you get the bill in terms of money and in terms of CO2 impact, then you get more awareness of that. No? And in the context of machine learning, I think that something similar should happen. A change of mindset should happen. So there is also a very good tangible awareness of the effect of the models that you're developing, because it seems that now people are just trying to build larger models with more data and more parameters. And we are, as it has been reported in many places, now we are at a point of diminishing returns. You're multiplying by 10 the number of parameters and, of course, the cost to improve 0.1% the performance. Well, maybe that's not worth it, right? Maybe we should be smarter in thinking how we're actually using our data and our resources in order to obtain the best return from the energy that we're using. And the transfer learning, for example, is one of the things that we should be doing much more. I mean, sometimes people are not aware of how much you can actually save in terms of computing time, a factor of 4, a factor of 5 in many cases, just by using transfer learning. And then another thing is that we should, anything that we know about the problem that we're trying to model, we should embed in the model, right? So if we know that the problem is periodic, if we know that the problem is symmetric, if we know that the problem is incompressible, all those conditions should be part of the model. They should be embedded in the model. Yeah. Because, first of all, the model may or may not learn eventually that the problem is symmetric, that the problem is periodic, but it will not learn it perfectly. It will learn to a certain loss that you said, right? So it will not learn it perfectly. But second, the amount of data and training time that has been used to learn those properties of the problem is wasted because you already knew them in the first place. So you will come up with much better models and much more efficient and environmentally efficient models if you're able to embed those properties in the model that you're developing. So I think that's a very important change of mindset that is needed towards the next years if we want to really have AI for sustainability, but being aware of the sustainability of AI.
Interesting. Ricardo, how much is the government actually spending or like putting money into these research projects? Because I've known, and maybe correct me if I'm wrong, you've recently gotten a grant, which is a very prestigious grant, working on deep reinforcement learning for flow control and turbulent flows. So maybe talk about maybe the aspect of government supporting you in that aspect, but also why deep reinforcement learning and what are you actually working on? Like, it's a big question, I know, but maybe you can elaborate on that.
Yeah, thank you. So there is certain interest, of course, in applying these methods. The grant that I got is from the European Research Council, the ERC, which is an excellence program of the European Union, where they fund not only machine learning, they fund any area. No? It's a very wide range of areas of science that is being funded by the EU. And I mean, I have seen an increase, of course, of the projects that have to do with data-driven methods, with machine learning that are being funded, but not necessarily over other areas, because, of course, sometimes people are just trying to use these sort of methods because they think that they will increase their chances of being funded, and that's not necessarily the case. You should choose, and that's a little bit what I mentioned at the beginning as well, you should not use machine learning just because you want to use machine learning. You should find the right application and use the right algorithm for that application. And if it turns out to be the best one, then you will have chances of being funded maybe, and then you can be lucky, but not for the sake of just doing machine learning, because that's, I mean, I think that now funding bodies and the review panels see through that very easily. They can see when an application, they just, throw machine learning because it looks fancy, but it doesn't make any sense for the problem that you're trying to solve. So I think that if you have a good problem that can really benefit from machine learning, then that's a good fit. If not, you should just stick to other methods that are less expensive computationally and perhaps a little bit more suitable to the application that you have. Talking about reinforcement learning, the idea of the project is to use high-performance computing. So we're going to use very finely resolved simulations of turbulent wings, and we're going to use reinforcement learning to control the flow around the wings. And this has to do a little bit with what I was mentioning. Sometimes when you want to set a boundary condition, you don't know exactly what should be set. When you want to control the flow, you also don't know exactly how to control it. There are some approaches what we want to do, of course, is to minimize the drag while maximizing the lift. So we want to really have a much more efficient wing from the perspective of aerodynamic efficiency. And turbulence is a big factor. You want to reduce the turbulence activity, but at the same time, you want to keep the flow attached. And at the same time, you want to have a minimum pressure drag. So you want to have boundary layers that are not increasing the thickness of the wake too much. So there are many factors. And it's not a very... Just controlling turbulence is difficult enough, but when you bring in all these additional parameters of a wing, then it gets very, very difficult. No? So there are some approaches like opposition control to control turbulence. There are some methods to try to attenuate certain scales in the near world region, in the outer region, but there is not a clear strategy on what should be done. And then through reinforcement learning, which has been a method recently applied over the past years to control very simple flow cases, there has been some promise because in reinforcement learning, you just set a certain reward function, a certain goal, in this case, minimize the drag or maximize the lift of the drag. And then the agent, the reinforcement learning agent, through interaction with the system, tries to try different possible actions that can be applied to the system and eventually, hopefully, reach a certain policy that tells you, given the state of the system, what should be the action to be taken in order to reach that goal of minimizing the drag or maximizing the aerodynamic efficiency. So the advantage of reinforcement learning is that you are not telling the system how the control should look like. Yeah. You're allowing the agent to discover that sort of control. And in simple flow cases, there has been some evidence that these reinforcement learning approaches are outperforming classical methods for flow control. So there is quite some promise. And I was lucky to be awarded this grant to try this in more complex cases, in turbulent wings, a high Reynolds number with quite some geometrical complexity. So we can try to see the extent to which reinforcement learning is actually helping us to achieve novel control strategies that can maybe be discovered through these approaches.
Really interesting. Ricardo, maybe a mind-boggling thing for me at least is, or maybe the question that follows up is, there have been so much people researching this, like, for example, how the wing should look like, how to maximize lift, how to reduce drag, things like that. Like, where's the end goal? What's the end goal? At some point, you reach a limit in terms of what you can optimize in terms of a wing and the turbulence around it. So what's the end goal?
I think it would depend a little bit on your application, because of course it's not the same if you are aiming at having a laminar wing, a laminar wing in which of course you have very little drag, but then you may suffer from separation more easily because you have less momentum close to the wall. So perhaps in certain applications the laminar wings are very, very good, but then maybe for others, that would not be the optimal solution. If you're trying to optimize your system for takeoff or landing, where you have, in those cases, the lift-induced drag, the drag that is produced by the wingtip vortices. So when you have the wing at the tip, you have, due to the pressure difference, these vortices that roll around the wing. In those configurations, in takeoff and landing, 80% of the drag comes from the lift-induced component from those wingtip vortices. So then maybe the situation that you want to optimize is different. If you want to minimize the drag in that case, or if you want to optimize for a turbulent wing in cruise conditions, where you want to have turbulence, because you want to be robust enough to separation, but at the same time you want to have sufficiently low skin friction, and trying to have little pressure drag as well. So there are so many variables that come in, and so many modes of operation as well. When you're experiencing a whole flight, and different flight conditions. If you're looking at a commercial aircraft, but that's going to be very different if you look at drones, for example, because the scale is very different. UAVs and UAMs, in general, the whole urban mobility revolution that we're experiencing, where there is quite some potential, and then the physics is, again, completely different. So you want to optimize the wings in a completely different way. Or if you want to consider helicopters or other types of devices, then the optimization changes a lot. So I think it's, we are able to design better solutions with these supervised learning and reinforcement learning approaches. we are getting very promising results. But then the complete potential will depend a bit on the application that one is considering. We're trying to develop methods that are robust enough to be applied in many different areas, but hopefully we can actually have solutions that can be general enough and that can be applied by other people afterwards. That we can really have these algorithms, these methods, and that someone else can really come and use similar approaches to solve that problem.
Yeah. Is there an outlook from Ricardo, the guy himself, like for 5, maybe 10 years? What can we expect in terms of artificial intelligence for fluid mechanics?
Yeah, I think one area that is quite promising, well, first of all, I would like to mention interpretability. We talked a bit about explainability and interpretability, and perhaps the biggest difference is that explainability is a term that is used to denote when we can get some insight into the predictions. So we can actually, and this is, for example, the Shapley values, methods in which you are perturbing the input, and then with variations of the input, you can see what parts of the input are affecting the output the most. Mm-hmm. So with explainable deep learning models, you know what parts of your input image, for example, are more important to the outputs. It's about the relevance of the input towards the output. Whereas interpretability is a stronger requirement. In interpretability, you really want to see exactly how the input and the output are connected, which is not the case of explainability. Yeah. And in that case, an equation is interpretable. And there is quite some work in symbolic regression in the context of deep learning where you can get that interpretability. I think the first area where I think in the next 5 years we will see quite some promise is in interpretability. So being able to really develop deep learning models that are interpretable, that you can really see exactly what the models are doing when you apply them to fluid mechanics, and that you can hopefully learn something about the physics. Because what has been shown is that these interpretable models are also able to generalize better, because you can actually account for more parameters, and you can actually see that you can apply them to a wider range of conditions compared with more classical deep learning models that are not interpretable. So that's one area that I think is quite promising. Another area that recently has started to emerge, and that I think that there could be some interest, is generalist agents, like in the case of Gato, the algorithm that has been recently developed by Google DeepMind, which is quite interesting because at the end of the day, this is based on language models, which is quite interesting, because just training these transformer-based models for language processing, which is in principle just one task, but that task is so general that it's actually able to do a very wide range of tasks from that initial training that has been done. For example, just by showing how to complete text, these models are able to translate. Right? So you know how to complete text, therefore you know how to translate languages, but they can do also mathematical operations. The model has not been trained to do mathematics, but through text training and knowing what the sequence looks like, it learns how to do math. Gato goes one step forward. And this algorithm, which is quite general, can do a very wide range of tasks, not as well as the models trained specifically for each of those tasks, but it can identify images, it can produce text, it can play Atari games, it can do coding and mathematical operations. So it's quite, I think it's quite impressive what has been achieved. I think that the transformers in general are giving us quite some promise that we are not fully exploiting now. In the context of fluid mechanics, we have been using transformers for both temporal and spatial predictions. So we are actually able to outperform recurrent networks in temporal predictions and CNNs and GANs for spatial predictions. So transformers, I think that they are giving us quite some promise. And in this direction of generalist agents, in this direction of being able to do many tasks with one single model, I really think that we will see quite some interesting developments in general in AI, but in particular in the context of the application of machine learning to fluid mechanics.
That sounds like a very promising outlook. Thank you so much, Ricardo. One last question I have, because I have to run to another meeting, you probably as well, is looking back to your student years, with your knowledge you have now, Ricardo, what would you advise your younger self in terms of studying? What topics would you like to pick? What courses, online courses would you like to choose? Maybe some recommendations to your younger self. Let's put it that way.
Yeah, that's a good question. I mean, I liked my studies because they were quite general. So I studied mechanical engineering in Valencia, in Spain. And there the degree is very, very general. You study a little bit of everything from, of course, fluid mechanics, but you study structures, solid mechanics, management, business. You do everything, no? And I think that such a general approach is good because you get exposed to many different things. And then later on, when I moved to Chicago, I did my master and my PhD at IIT, the Illinois Institute of Technology. There I really learned more and really loved the fluid mechanics, the turbulence, aerodynamics, all these things. So I think that perhaps if I had the chance, I would have liked to start doing more fluid mechanics, even more at an earlier stage. But I'm not. I mean, I'm happy to have this generalistic approach, and I think that that's good for students who are starting and they're doing their engineering degrees. Do not focus necessarily on one particular topic, because sometimes the solutions that you can find for one area can be very, very helpful for another area. So to keep an open mind, I think, is very important, and to have a strong mathematical background. I mean, that's always going to help you. That's always going to be interesting, because you will understand things at a much deeper level that will be much more helpful. And of course, coding, which now there are so many resources nowadays. So I really encourage all the students to spend time learning about the mathematics, learning about the applications in computer science, in coding, and developing your own codes, because it's fun. And also it is something that will make your life easier in the future if you want to work with science and all these very exciting topics.
Yeah. Is there any strengths or weaknesses, maybe, Ricardo, in terms of what you see maybe when you supervise students, where you say, this is, for example, you should be more strong in linear algebra, or maybe, as you mentioned, in coding? Is there some recommendations that you can give to the audience?
It depends a lot on what you want to work with. But if you want to focus on these areas, of machine learning, fluid mechanics, turbulence, I mean, I think that the mathematical background is very important. I mean, that goes even before the coding. You really should know mathematically what your models are doing, and you should understand them at a deep level. That's the first thing. You should understand the mathematics. And second, there are so many libraries available for everything, for neural networks, for any machine learning model. But you should try to implement these models yourself first. So you should really see how it works, see really the challenges of implementing them, see the typical bugs, because then you will fix them and learn how to find them later on. So try to spend time doing the code yourself, and try to spend time really fighting against the code, because that's really the experience that will help you in the future, when you are developing and tackling more complicated problems. And of course, enjoy also the beauty of science. I mean, I think we are in a time where there is some debate also about the stress and the pressure of the scientific work, both for the students, for the supervisors, for everybody. And sometimes we forget a bit the beauty of it, that we can really tackle very amazing problems, and we can really have great colleagues, great conversations, very fun conversations. So I think that's also something to really focus on, and to really be very happy about, and great conversations like the one that we're having today. So I think that this is also one of the positive sides that we should not forget of the work that we do when we're working with science.
Beautiful. And Ricardo, I would like to thank you so much for being on the show. I had a ton more questions, as you know, from the audience that sent us a ton of questions as well. So I'm promising we'll have a second part in the future.
Excellent.
I really enjoyed the discussion, and I wish you an awesome weekend. And thanks again for being on my show. Really enjoyed it.
Thank you very much for the invitation, and a great weekend to you too. Bye-bye.
Bye-bye.